So we can start the introductory slides. So I will also want to do these things live. And then I will do a review of 348. And then I will, if you have any questions, of course, I will stop at 30. Okay, I looked at the time. So we have 4 minutes, but I will start. I need water. And then content, I expect the content to finish on time. So we will be done for this session. Okay, so I will give you some introduction, what we are doing, what are we learning. The resources for this introduction are actually these 2 courses. I put them here for a reason, because these are similar courses, okay? So you can also look at it. There are certain quite famous architecture courses. You can follow it. Their lectures are open. And a third source is, I really like this book. I might a little bit use it for 446 as well. Computer Architecture Quantitative Approach. So there is a very famous series of books of Hennessy and Peterson. This is the one that has some analytical models and so on. Okay, so I like this book. Okay, so now what are we trying to do? There is always some technology change. People invent new ways of building semiconductors, new ways of building these very, very small components for computation. So the technology is evolving. At the same time, now there are applications that are using this technology, and applications are evolving as well. And there is always a interplay with what people want and what technology offers. So normally what happens is that technology offers a little bit more than what people want, because people cannot imagine that they can do these certain applications, certain things. So there is some excess technology, let's say that, and then applications immediately catch up. So they utilize the technology in full, and they want more. Then the technology has to catch up again. So there's always this interplay. So how do you make the physical possibility of computing available to the final application, the application that I'm talking about, that we are doing this WebEx right now, for example, or you are using MATLAB, for example, okay, such things. So how do you bring this semiconductor transistor level development to that? So there is this very famous, not famous, the fundamental concept in computer system design. All my slides have this. Whatever I am teaching, whatever I am talking about, after some time, all these things look similar to you, because they are, all these things means that I am teaching logic design, I'm teaching this architecture, I'm teaching computer networks, I'm teaching graduate courses, okay? I'm designing things. They all look similar in the sense that the whole idea is about abstraction, modular design, providing clear interfaces, okay? So what happens is that there is all this layered structure on top of the technology to bring it to the application. So the semiconductor is abstracted out from this WebEx using this layered architecture. And I will go through this layered architecture, and in the end, I will also map them, which I always do in the options seminar, to what we are doing in our department in 10 minutes, 10-minute break. Come back at 40. Okay, so we go on. So now we are looking this very famous layered computer architecture picture. You see this in many resources. Okay, so I took this from one of these courses that I put on the slide. So we will go through these layers. So the application here in this example, that you want to write some piece of code that is sorting an array of numbers. So you give some unsorted thing and then it gives you the sorted output. So now you need an algorithm to realize this application. The application is executing a task. So we have an algorithm to realize that. So what you can do is you find the minimum in the array, in the unsorted array, and then you move the minimum into an output array. And then you keep finding among the remainings, you keep finding the minimum and you move them to another array. So the output array is finally sorted. As a teaser, I tell you that in EE445, you will learn all kinds of sorting algorithms, okay? But it's not the subject of this course, it's just some example. Then you can implement this algorithm, which is total mental construction, in using some high-level language like C. Okay, so this is the C code for it. So we are now at this layer. Now, the computer architecture part that we are going to discuss in this course is this red part. So instruction set architecture, microarchitecture, register transfer level, and so on. So there is an interface between what we wrote, the application is using a high-level programming language, and the instruction set architecture that I will tell what it is, but it's basically describing how the machine really works to a programmer. There's an interface that is called an operating system, and it's a program itself, software, and it handles low-level hardware management. So Windows is an example, Linux, Unix are examples of the operating system. Now we are coming to what we are talking about in this course. So there is a concept called the instruction set architecture. So for this one, the idea is that it is basically expressing the structure and the behavior of the computer as seen by the programmer of the high-level language. So it is basically the structure is of the so-called assembly language, okay? So the instructions and so on. But the instructions, the machine-level instructions, can be implemented with different circuits. You can design, we will see how these circuits are designed in this so-called basic computer. So we will see one way of implementing it, and you can think, oh, I could implement this machine level instruction, this low level instruction that is going to be an output of the translation of the C code. Okay, this instruction I could do it with a different circuit. You should think about this when we are talking about this basic computer part. So how you really implement the instruction set architecture is called the microarchitecture. And you can have different implementations of the same instruction set architecture. So this slide is showing you a certain instruction set architecture output, okay, of what would have happened regarding that C code, how the C code would be compiled into the machine code, okay? So this is a certain architecture. At the end of this course, in the last 2 weeks, we will look at the certain processors instruction set architecture. So it is the interface that is shown to the programmer, the interface that shows how the hardware behaves to the programmer without showing the hardware. The hardware itself, the circuits themselves will be the so-called microarchitecture, and we will learn about all these things in this course. the instruction set architecture and the microarchitecture and how things are done in the register transfer level. So we are focusing on these pink layers, demonstrating the idea on this fictitious basic computer of Manos old book. Then everything will be ported to ARM, to a real processor, towards the end of this course and in EE446. Okay. So the instruction set architecture, because it's what we are talking about all the time and it's a new term, it represents all the necessary information to write a machine language program that will run correctly on the machine. The machine language program is normally the output of the compiler, but you can also, which you will write, and in 446 labs you can write machine language program yourself. And it describes the conceptual structure and the functional behavior of the certain hardware. It abstracts away, because we love abstraction in the computer design, because these are actually very advanced and complicated things. So we always divide them into pieces and hide the internal operation from the users of it. So it abstracts away the organization of data flow and control, the logic design and the physical implementation of the machine. And as I said, there are many implementations. There could be many implementations of the same instruction set architecture, and they could have different cost and performance, but they would run identical software. So what I'm trying to say is that your compiler will produce exactly will produce some set of instructions like we have seen in the previous slides. I run these instructions on this machine. They run in 1 hour. I run these instructions on that machine. They run in 1 second. Okay? Because the second machine is designed much more efficient, much more advanced, and so on. So it can run faster, but the outcome will be the same. The output will be the same, the correctness, everything, it will exactly be the same because it's the same code, but will run on different hardware platforms. So instruction set architecture includes the addressing modes. We will learn what this means. Operand specifications, operation specifications, control flow instructions. We will learn all these. Going on, now register transfer level you actually learned in logic design. So you will see it now when I'm doing the review. So register transfer level is describing how the bits, the data is going through the system. And then gate level, how you build the circuit using the gates. And the circuits, devices, and the technology is basically the silicon. Okay? So now this is my slide in computer options seminar. How do we address exactly this layered architecture in our department? Now think about this. Regarding the physics, so the semiconductor, you have a dedicated semiconductor course, 212. Then when you take digital electronics on top of this, you learn by how to build the basic circuit blocks using transistors. Then but you still have current, voltage, things like that. Okay, 312. Then we cut all the relationship with the current, voltage, that kind of physical things. We abstract them out. It's exactly what we are doing. Okay, we abstract those details out, and now we have gates at our hands with well-defined inputs and outputs. So we learn about gate level design and register level design in logic design. 348, that's where you are now. Then on top of this now, starting with this course and the next semester, we will learn how to realize an instruction set architecture with a microarchitecture by these building blocks, circuits and gates and registers. Now in 447, we will also, as I said, learn some advanced stuff regarding pipelining, caches, and so on. In 447 microprocessor course, you will learn the instruction set architecture of a certain processor, and you will learn how to use it, how to make the processor do the task that you want to do. But you will not know how the processor itself is doing it. Okay, so you will not learn the architecture of the ARM processor in detail, but you will learn how to use it in 447. Now we have operating systems course. So that course will directly address the operating system. It's in the second semester. And regarding the higher levels, so programming language, algorithm, and application, we have data structures course that is basically addressing all. And we have this intelligence course, which is also basically addressing it's an application. It is using some algorithms to achieve some tasks, and it comes with some programming, as far as I know, assignments. So it is addressing these top 3 layers. So we have, of course, since we are in the EE department, the major focus is on the architecture part, but on top also, especially with data structures and operating systems, we are completing this picture. So I would say it is not very bad. Furthermore, we learn how computers work together using computer networks course in the second semester. In microprocessors, you will learn all this device interfacing and so on. So how do you put things together, pass information among them? And for 446, there's all multiprocessor components. So it also addresses how you make multiple computing devices work together. Okay, so additional to this stack, we have basically a dedicated course in the second term that describes how many computers can work together in a network. That's also strictly computer course. Okay, so now we will learn this basic computer in this, I told you, from the Manos book and so on. And the very interesting thing is that it has all kinds of operations that are present in the contemporary processors, okay? It has the representative operation for every class of operations that are available now. So what I'm trying to say is that there are all these different classes of computers. We have all these handheld devices, mobile devices, we have desktops, we have servers, okay? And we have all kinds of embedded devices. Now, if we look at why we have these different types of devices, is that we have personal mobile devices because people want to do things continuously real time, okay? So the idea is that people want to, I don't know, they want to browse the web, or they want to, maybe you can use WebEx on your phone, right? So you can do all these things real time when you are walking and so on. So it has to be also energy efficient because it's not always plugged into power. Whereas for desktop, the emphasis is on price performance. So if I am running MATLAB code, I would run it on some desktop, or I would run it on my laptop, okay? So I won't go try to run it on a mobile device. I don't know if such thing is possible, but I won't do that. Servers are basically more designed for availability and throughput. What it means is that a server, you will learn this in computer networks, a server is a computer which is not horribly different than a desktop, but it is designed such that it is always on, and many other devices other computers are connecting to the server to collect information. Okay, so it should be able to serve, it should be able to provide information to many devices, it should be able to scale to many devices and provide a lot of throughput. Warehouse scale computers, so these are for if you think about it, servers that would be available in a cloud data center. So that is also what I'm looking in my research right now. So how do you give how do you instantiate virtual machines on this kind of servers in a cloud data center such that the user can use these things as if it's their own computer, right? And there's also this Internet of Things, embedded computers, wearable devices, right? So these are computers that don't look like a computer. So they don't have a screen, keyboard, whatever, but they are actually, they have CPUs running inside. And they will all run something that is in common with our basic computer. Now, regarding the performance and the trends in the computer architecture, if you look at it, this is a very famous graph. It comes every time. This is taken from Hennessy Peterson book. So it shows that the performance in terms of computations, as far as I know, the y-axis should be number of operations per second. Okay, and the x-axis is the years. So this capability of computing increased by time over the years, quite fast, Moore's law and so on and so forth. Now it turns out that around 2003 or so, the gain that you could get by jacking up the frequency of these processors, it kind of died. Okay, so the growth of this curve slowed down by just simply jacking the frequency up. So people had to look at different tricks, different ways of playing with the architecture to improve the performance since then. So the integrated circuit technology, it grows with a certain percentage. I mean, these are the fundamental components, okay? So the DRAM capacity is growing with a certain percentage. The flash capacity is growing with a certain percentage, magnetic disk, and so on. So there's always an advancement, but depending on the available technology, the advancement speed is not always at the same rate. So then if you cannot catch a certain rate, then you have to invent tricks such that you can fulfill the application requirements. So now this legacy view of computer architecture, they were focusing on the instruction set architecture design. So they were thinking like how many registers, how should they be connected, how should we do the addressing, the different addressing modes, how should be the operands formatted to pass to the instruction, what kind of operations, what kind of controls should we have, and so on. Okay, so we will learn about these things, but they were the core topic. Now, people also focus on how can we maximize the performance within constraints such as cost, power, and availability. Okay, so when people are building the architecture, they're also looking at these things now in more detail. Now, performance metrics, I want to go over them. I hope to revisit these metrics in 446 in detail, okay? So the typical performance metrics for some computer would be, one is the response time. So you give a task, compute this, and then when is it completed? So how long does it take? What is the latency? The other metric is throughput. So your latency could be very long, but once you take out the first task, then you take a task out, you take some result out every clock cycle, for example. So your throughput is this number of tasks per clock cycle, but you overlook how long it actually took to compute each result, okay? But you see that the results are produced back to back. So that is throughput, total work done in a given time. Then you can look at the speed up. So you have a machine and somebody comes with another machine. So you can look at their execution times of the same task. Okay, so which one is faster? Now, regarding the execution time, there are two terms. So one is called wall clock time. It includes all the system overheads, like it's real how much time goes on the wall clock, okay? CPU time is how much the CPU spent on this. Because wall clock time includes all kinds of disk accesses, IOs, and so on, okay? So CPU time is defining the performance of the CPU. And people use benchmarks. These are special pieces of code to test the CPU. So there are standardized pieces of code that maybe don't produce any meaningful result, but they have a certain sequence of instructions in them to test your machine's performance. But I would like to visit this in more detail in 446. So this concludes my introduction for the lecture. So I hope I could give you an overview of what we are going to do for the semester. Now I want to go over your logic design, okay? This is going to be fast, not very, I mean, my purpose is, I am not trying to teach you logic design because you already know it. But I want you to remember certain concepts that we will use, especially regarding registers and timing, okay? So, we will use registers a lot for computer architecture. So, obviously, we will represent numbers in them for arithmetic and logic operations. So, you remember that we represent numbers in registers by using some certain conventions if it's a mathematical number, or I mean, if it's a number that shows a certain quantity. And when we have a register of n cells, then it can be in 2 to the power n possible states. And we have methods of showing numbers in these registers. So we looked at how we can represent numbers with signs in the register. So we have learned something called signed binary numbers in two's complement. So that is what we are going to stick to in this course. So we know that in the register, the most significant bit shows the sign. So if it is 0, then the number is positive, and the magnitude of the number is directly given by the number. If the number is 1, then we understand that the number is negative. Machine also is constructed with that convention. And the magnitude is the 2's complement of the number, where 2's complement is defined for an n-bit number of base, this is base 2, so this is R's complement. N-bit number 2 to the power n minus the number magnitude itself. So if I have an n-bit register with value x, then the x, according to this signed 2's complement, x has to be in this range. So if n is equal to 5, these are the numbers I can represent. I can represent from minus 16 to plus 15. So if you think that we are going to have in the basic computer 16-bit words, so this is basically then what you could represent would be minus 2 to the power 15 and plus 2 to the power 15 minus 1. So these are certain examples. So this is how you have plus 5. I know this is plus 7, and this is plus 9. And if I want to have minus 7, and then if you think about it, this fits the description. This is basically 16 minus 7. So this looks like a 9. Okay, so and we also learned the methods to convert the number to its 2's complement. So we learned arithmetic addition by hand. We learned all these rules. So for a 5-bit register, we looked at possible cases. We discussed overflow. Okay, so we know how to do arithmetic addition in 2's complement. Now, regarding the number of bits, we should be aware of that. So if the number of bits in the register is not sufficient to represent the number, then we have overflow. And we can extend, if the quantity that we want to represent requires less bits than the register length, then we can extend it by adding bits to the left. So we copy the value of the sign bit to the added most significant bits. So the number will not change, but it's just representing it using more bits in the bigger register. So you can have a 4-bit representation of 3 and 8-bit representation, 4-bit of -5 and 10-bit -5. Okay, so this was the arithmetic. Now we are going to, for the basic computer, starting with ASM, we are going to design circuits. The circuits will be sequential circuits together with the combinational parts. So we will need this gate level simplification. So it is 348 again. So we learned this K-map. Okay, so we learned K-map for 3 variable, 4 variable, 5 variable K-map. So the idea was that we had some layout in the gray code format, and we were writing the variable combinations that the function gives a 1 in these squares. So 3 variable K-map, the layout was like this. So each square represents a min term where you have 3 variables. And we were enclosing the adjacent min terms with rectangles. So we needed to know which rectangle is adjacent to which rectangle. So for 3 variable, it's obvious. And here and here and this and that are also adjacent. So the map was rolling around. And we had the 4 variable K-map. Again, there's a layout. So when we are simplifying, if there is and we need to know again who is neighbor with whom, especially these corners, right? So this, they were all neighbor to each other. So the map rolls around. 5 variable K-map. We might have something with 5 variable K-map, okay, in the homework or in the final, to have some a little bit advanced question. So again, you need to know the layout and you need to know who is neighbor to whom. So for 5 variable K-map, also the squares in the same position in this 16 squares are adjacent to each other. So MK is adjacent to MK plus 16. So M3 is adjacent to M19. So it rolls around and it's also on top of each other for these 16 square parts. Okay, now we learned that there are 2 types of circuits, combinational and sequential. So the combinational circuit was the outputs only depend on the input, and the outputs are produced immediately when the input is applied after the signal propagates through the gates, okay, without any more wait, whatever the gate propagation time, how many gates you have back to back, but the output is produced. So combinational circuits only use logic gates, whereas the sequential circuits, the circuit output depends on the current input and the past combinations of input. So we will look at everything clocked, okay? Nothing asynchronous for 445, 446. So the output of the circuit in a certain clock T plus 1, let's say, will depend on what was stored in the memory elements, the state of the circuit at clock cycle T, and what input is applied externally. So we also looked at how you build memory elements in the sequential circuit part. So we will come to that. Now, first, I will remind you the relevant combinational circuits. Okay, we will use these things in architecture. So we will do arithmetic operations. For that, we will need something that we call this full adder. Okay, so full adder was a combinational circuit with I'm looking at one bit of it, okay, with 3 inputs and 2 outputs. So it takes 2 operands, 2 bits A and B, and a carry input from, if such thing exists, from a previous stage of the adder. And it generates a sum and carry out. So we actually built this by starting with the truth table. So according to the values of A, B, and carry in, what should be the sum and what should be the carry out. Then we started extending these things. So how do you get a parallel adder? How do you get a 4-bit full adder? So in that case, if you look at this circuit, this is a single block. It is getting a carry in 4-bit adder. It is getting a carry in 4-bit operands, addends, and it is generating a 4-bit sum and the carry out. So we also said you can cascade these things. So there's a carry in, there's a carry out for 4 bits. These are parallel. So you see that 4-bit operand A, 4-bit operand B, 4-bit sum, and this generates a carry out. I plug in the carry out to the carry in of the next, and now I have an 8-bit parallel adder. So we already learned how to build circuits from predefined components, because here there is a remark which says that direct design would need, using the Karnaugh maps and simplification, right, 2 to the power 9 input combinations. We will use full adders for the arithmetic operations. Now we learned this certain combinational circuits. Okay, we learned encoder, decoder, multiplexer, and demultiplexer, right? So for 445, the important things are decoder and multiplexer, which basically are related to these other 2 as well. But we will explicitly use these guys. So decoder is a combinational circuit. It has n inputs, 2 to the power n outputs. And we are looking at this line decoder, which is actually the min-term generator. So it looks like this: 3 inputs, 8 outputs, and only 1 output is 1 at a time. Look at the truth table. So when x, y, z are 0, 0, only d0 is 1. When these guys are 0, 0, 1, only d1 is 1. According to the input xyz, one of the outputs from d0 to d7 will be 1. And if you look at it, d0 actually is 1 when the min term x prime, y prime, z prime evaluates to true. Okay, so basically it is this so-called min term generator. So this was one component that we learned in 348. We will use it in 445. And as I said, only 1 output is 1 at a time. The next component we will use is a multiplexer. So multiplexer is composed of 2 to the n inputs, 1 output, and n select inputs. So the select inputs define which of the 2 to the n input lines will be connected to the output. So according to the value of select, you will see the value of one of these 2 to the n input lines at the output. That's the whole deal. So if I look at a 4 to 1 multiplexer as an example, now I have 4 input lines. So to select which one will appear at the output, I need 2 selects. So if you look at the truth table of 4 to 1 multiplexer, if selects are 0, 0, output is showing I0. The selects are 0, 1, I1, 1, 0, I2, 1, 1, I3. So this will come back in ASM. Actually, I can write the output of the multiplexer as in this form. So S1 prime S0 prime I0, S1 prime S0 I1, S1 S0 prime I2, S1 S0 I3 is my output, depending on the selects and the inputs. Okay. Now, so we have up to now, I said I need to know about numbers. I need to know how these basic combinational circuits work. A full adder, a decoder, and a multiplexer. Now I will a little bit talk, and I should remember the Karnaugh maps because I will design these circuits. I want to minimize things. So now we will talk about sequential circuits. Now the sequential circuit has a combinational part and memory elements. So the memory elements store information, and they produce feedback for the operation of the sequential circuit. If I look at it, I have n external inputs, m outputs, but outputs are produced according to the state that is stored in the memory elements and the external n inputs. Okay, so we learned this flip-flop, which is basically the major memory storage building block. So for a flip-flop, I'm storing 1 bit. This 1 bit, we constructed this from this feedback of the NOR gates. Okay, so we had this latch, and then we added the clock and so on. I'm passing all these things, okay, abstraction. I am focusing on what we need, the detail we need for 445. I don't need to build the latch for 445. So for flip-flops, now I am storing a certain bit, 1 bit, in the flip-flop. It is what I see at the output. My present time is t. I'm counting clock cycles. I am in the clock cycle number t. Okay? The present state of the flip-flop I denote it by Q of t. Whatever I will see at the flip-flop output in the next clock cycle, Qt plus 1, that is going to be produced whatever is ready at the flip-flop inputs at time t. So the next state of the flip-flop is ready at the inputs at time t, and then at t plus 1, when the clock hits, that next state appears at the flip-flop output, and the following state for t plus 2 is ready at the flip-flop input. So the timing, I will come back to this. So if you think about this, Q of t plus 1, we built all these flip-flops. The next state is represented algebraically in terms of its present state and the present input. What I mean by inputs are now the inputs of the flip-flop. So I see the single flip-flop as the sequential circuit. So for D flip-flop, for example, the next state, what you will see in the output Q will be output Q at t plus 1 will be what you see at the D input at time t. Okay? So next state is sitting here, present state is here, clock hits, next state appears here, and t plus 2 is sitting here. So we learned all kinds of flip-flops. So we will use D and JK mostly. So I will just remind you. Let's look of the D flip-flop. So that's the characteristic table. It is basically describing Q of t plus 1. The next state is a function of input D and the present state Q of t. And simplified characteristic table says that if D is equal to 0, Q of t plus 1 is clear. If D is equal to 1, then it's set. And then there was this thing called excitation table, if you remember. And the idea was, what should I provide to the input of the flip-flop such that from a certain given present state, I travel to the desired next state. That was the idea of the excitation table. So that is what you have for the D flip-flop. I simply basically give whatever I want to see as the next state as the input. Same thing for JK. Now JK has two inputs, obviously one output Q. And we looked at the characteristic table. So the function is JK00, no change, 01 reset, 10 set, what you will see in the Q output I'm talking about, and 11 is toggle. And the excitation table describes that if you want the state combinations, TT plus 1, J should be like this, K should be like this. Okay, then once we have the flip-flops, we built registers as sequential circuits. Now, I'm not talking about just the mathematical notation. So an n-bit register has n flip-flops with n bits of information. And it is augmented with a combinational circuit which determines the control. So what you do with this n bits of information that is controlled by a combinational circuit. So this is the simplest 4-bit register. I am constructing it with D flip-flops. The inputs are A3 to A0, most significant to least significant. Outputs, the Q outputs of the çok özür dilerim, I'm so sorry. The inputs are I0 to I3. They are ready at the D inputs. And the outputs are A0 to A3. They are at the Q. So that is the input information. And that is what the flip-flops store. These are all clocked. Everything is clocked. Now, for this very simple implementation, there is pretty much no control. So when the clock hits, whatever you have, this I0, I1, I2, I3 at time t, they will appear at A0 to A3 at time t plus 1. Then, with this basic structure, we added the combinational circuit, okay, together with the multiplexers, and we generated the control inputs. So now this bidirectional register, the control inputs are S0, S1. They describe the operation. So S0, S1, 0, 0 means the content of the register is the same, which means I am reloading the content. You can do shift right. We learned this shift register, right? So we can do shift left, providing external inputs for shift right and shift left. And you can load externally in one shot 4 bits that are provided as the parallel input. Okay, so this is universal bidirectional shift register. Then we learned counters. Okay, so we learned how to build counters using the registers. So here I have a 4-bit counter, again, with control inputs. There's an asynchronous clear, whatever the clock is doing. So you could do it in the middle of the clock pulse, but you can clear it, make it 0. You can load the counter with a certain external value, or you can make it count up increment by using these control signals. Then using these counters, this is very critical because we are going to exactly do this in the ASM, okay? And how we design the controller of the basic computer, okay? So what we need is some signals that are periodically repeated, A, B, that are related to other such periodically repeated signals in some sequence, okay? So first this signal happens, then this signal, then that signal, then that signal, and then again the first signal happens and go on. So how to generate different timing signals that are separated by a certain number of clock pulses and that are following each other. Okay, so we learned to do this by extracting the signals from the clock pulse. One realization was a 2-bit counter and 2 to 4 decoder. So for this 2-bit counter, I say always count up. I make the count 1, the count input. So the counter is counting 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. It goes in that way. Now, that is the input that is provided to the decoder, which we reviewed a little bit before. So when it is 0, 0, only T0 is 1. When it is 0, 1, only T1 is 1, and so on. So we learned this in 348. We will now exactly use this to build the control circuits of our computer. And this concludes my crash course in crash review for 348. So these are the basic things that we will use. Of course, we will use other things. Maybe I skipped certain things because they are not the fundamental thing, okay? But please have access to your 348 notes in case you want to revisit these concepts.